Friction! Friction is one of those great things. It allows us to walk around and to drive cars and things like that. But in other cases, we want to minimize friction. We use oil and wheels and things like that to make sure that things slide and roll and move with as little friction as possible. Sometimes it's great, sometimes it's not. But what is it and how can we explore it? That's the goal of today's lab activity, exploring friction. Now, to do that, we want to sort of understand what things might affect friction. Well, if you think about it, some surfaces feel grippy and others don't, right? Socks on a smooth floor, very smooth. But, rubber shoes on a carpeted floor, that's pretty grippy. You're not going to slide very well. So clearly the surfaces has something to do with it. And it's the combination of two surfaces, right? Like shoes on floor is definitely different than socks on floor, even though the floor is the same. So it has to do with not just the one surface, but both. And remember that friction is the force that prevents things or acts against things trying to slide, right? It is working opposes sliding force, sliding motion. So it's that definitely those two surfaces, they're touching each other. And if we remember that every time those two surfaces touch, there's also there's a normal force coming out of that interaction as well. Two surfaces pressed together. So maybe the normal force has something to do with it too. We can do a quick little experiment to find out. Take a piece of paper and a textbook or a book of any kind. If you put the piece of paper inside the book, right, pretty near the top, so there's not that much weight on top of that piece of paper, these two surfaces, the paper and the textbook pages, aren't pressed together very tightly, and it's pretty easy to pull that piece of paper out. But if you do the same thing lower in the textbook, so that there's more weight on top and therefore those two surfaces are pressed together more strongly, the paper of the textbook and the paper that you put in there, then we notice that, well, it's much harder to actually get that piece of paper out. In fact, if I push down on top of the textbook, right, then you're gonna rip the paper before you can get it out. It's fascinating. I haven't changed the surfaces. So the surfaces, right, shoes or socks on floor or carpet, right, definitely plays a role. But how tightly those two surfaces are pressed together, what we would call the normal force, that really also plays a clear role in determining how much friction there is. So let's explore those two things in this lab activity. We'll change some surfaces. Now we really can't quantify that, so we'll examine two different combinations of surfaces. But then also we want to change the normal force. All right, I have an idea. Let's set up our lab activity with a force sensor, a block with a couple of different types of surfaces on it, and some extra weights. You ready? Let's do this. So what we're going to do is we want to determine the friction force acting on this block as it slides across the table. But we also want to see how that is affected by the normal force between the block and the table. Now, as long as the table is flat, and as long as there is no acceleration up or down, it's pretty easy to determine what the normal force is between this block and the table. And that's just going to be given by the weight of the block. We'll modify that by adding in extra weights so that we know that the weight of the block and any additional weights on top is going to be exactly equal to the normal force between the block and the table. But then we also want to measure the friction force and how that friction force is affected by changing the normal force. And the way that we'll do that is by using a force sensor. Now this connects wirelessly to the laptop or iPad. And so what we'll do is we'll connect these two together, make sure that our sensor is zeroed properly, and then we will simply just pull our block slowly and steadily at a constant speed, or as near as we can manage. And I want you to think about why it is important, essential even, that we pull the block at a steady speed. Why don't we want it to accelerate? Think about that. You'll have to answer that question in your lab handout. So what we'll do is we'll determine the weight of the block. We can do that by hanging it from the force sensor. And then we'll modify the weight of the block by adding in weights on top in some known increment. These weights are marked in 1 Newton intervals, 1 Newton, 2 Newtons, 2 Newtons. We also have a 5 Newton. And as we pull on this block, we'll record the amount of force it takes to pull this to the right at a slow and steady constant speed. That should give us a very good way of determining the amount of friction force, our dependent variable. We'll have recorded our weight of the block as the normal force, our independent variable, and we'll be able to determine how those two are related to each other. Now, there's one extra little complication that we need to go into, and that's the difference between static friction and kinetic friction. Now, you may be able to figure it out. Static and kinetic. Static friction is friction when things aren't moving. That's the friction that prevents two objects from sliding past each other, from starting to slide. Kinetic friction, kinetic meaning movement, that is the friction when two things are already sliding past each other, and it's the friction that prevents them from keeping on sliding. It works against that motion to slow them down. Now, those are different things, and they behave slightly differently, and we have to take into account those different things when we're doing these measurements. For example, right now, this block is not sliding, and so therefore the friction between it and the table is going to be static friction up and until the point where it does start to move, at which point kinetic friction is going to kick in. Kinetic and static. Two different forms of the same concept, and they behave similarly but slightly differently, as we'll see. If I have this data collection set up, then when I hit collect and I start to pull on this cart or this force sensor, then I will see the force that it's providing to this block as a function of time. And I want to point out something really important. Okay. I'm going to hit collect and then start pulling on this force sensor, and that's going to provide the force recorded on the screen as a function of time, or the force provided to this block when it doesn't move, and then when it starts to move, and then as I'm moving it as well. Okay, so we'll see three separate regimes. So collect, and then I pull, and then slide slowly. On this diagram, we can see this is before I started to pull. So clearly, we can ignore all of that, not important. This section here is as I started to pull, but before the block actually moved. This would be the regime of static friction. And notice that value of static friction is anywhere from 0 all the way up to some maximum value on this graph of 3.84 newtons. Then once the block actually started to move, we entered the realm of kinetic friction. So kinetic friction is when it is moving, and we notice that force is roughly constant and is about 3 newtons, a little bit more, according to this graph. So that peak right here, that static friction peak, that's the maximum amount of force that friction can provide. But notice it doesn't have to provide exactly that amount all the time. If I only pull with 1 newton of force, then friction is only going to pull with 1 newton of force back, keeping it perfectly in balance. You notice this if you try to push on something that is sort of massive and has a lot of friction between it and the floor. You push a little bit and it doesn't move. That means the friction force is exactly balancing your push, however big your push is. That's static friction. It can be 0, like it is right now. There's no horizontal forces acting on this block. But it doesn't have to be 0, and it doesn't have to be some maximum value. It can be anything in between in order to balance out a horizontal push. If I pull sideways with 1 newton, friction will provide a 1 newton force in reverse. If I pull sideways with 3 newtons, friction will provide a 3 newton force backward. But notice that if I provide a force of over 3.8 newtons, 3.84 to be exact, then friction can't provide a force to combat that, and so boom, it starts to move. It accelerates because the forces become unbalanced. So for static friction, the value can be anywhere from 0 up to some maximum. And for kinetic friction, it is always one value as long as you are moving, no matter how fast you're moving. That's the model we're building here. We'll be collecting data points to determine a graph for both static friction and kinetic friction, and the slopes of those graphs will tell us something about the two surfaces we've chosen. That thing is called the coefficient of friction. And there's two values, one for static, one for kinetic. All right, so what you're going to be getting from me is a file for graphical analysis, an app on your iPad, or I guess you could probably install it on your computer if you had one. And in that file are going to be multiple trials. And each of those trials corresponds to a data set. And those data sets are going to be for the various measurements we do using the force sensor and this block. Okay? Now, one will be for table with a wood surface, so wood on the lab table, whatever that surface is. And that's going to be one data set. The first one is going to be just the weight of the block by itself, just hanging the block so you know how much it weighs, so you can determine the normal force between the table and the block. Every other trial after that, after the first data set, will be a pull at a steady speed across the table. I'm going to start from 0 and then pull out to some value. And that's going to be a steady speed. You'll be able to get a value for the maximum static friction force. That's the point you want, the maximum static friction force. And also the average kinetic friction force while the thing is moving. All right, I'll go over how to get those from your graph in a little bit towards the end of the video. All right, so let's start off with our first measurement. I'm going to 0 my force sensor and hit collect on there, and then hang the block like that. Okay. So from the end of that reading, you should be able to take an average value for the force sensor and get the weight of the block from there. I'm going to then 0 the force sensor again, and we'll do trial number 1, which is going to be data set number 2. And that's going to be pulling with a constant speed. I'm then going to be adding 1 Newton of weight to every single one of these every single time. So it's the block plus 1 Newton, the block plus 2, the block plus 3, the block plus 4, etc. You get the idea. I'll stop whenever I get tired. Probably we'll have 9 Newtons, which would be a total of 10 different data points to determine. All right, so let's do that. So now that we know the weight of this block, we're going to pull it with a steady speed across the tabletop. And as I increase the force, we'll notice that the force goes up to some maximum value. That's the maximum static friction force. And then as it pulls, it sort of hovers around some steady value. That's going to be the kinetic friction force. Now, that kinetic friction force is not going to be constant perfectly. I can't pull with a perfect, constant speed, and the table is not perfect. This model of friction has its flaws, it has its limitations, but it's mostly very good. So we'll see about this. The data is not going to be perfect, and that's going to be a great example to us of real-world application of data collection. All right, so let's start that up. I've got my force sensor. I will 0 it. Great, 0 the force sensor, and then we'll start with the first trial. Okay. Now I'm going to add 1 Newton to the top of this, and we're going to do it again, and again, and again, and again, adding up to 9 Newtons total. I'll try to 0 the force sensor whenever it's getting off of 0. And as we do that, I'll just fast forward through this bit because you don't need to see the details. You'll be able to examine the file after as I give it to you. All right, that's for the wood surface on the tabletop. We're going to do it again, but with the felt surface, this black felt, on top of some carpet surface. All right. let's do that. Okay, so we've got this set up. It's the same block, so the same weight as before. We'll be adding 1 Newton each time, and then we'll be pulling across the surface. We are now on a felt surface on top of this carpet. So having those slide across each other is changing the surface combination significantly, and we'll be pulling the same idea, pull steadily across the table with added weights on top. So this will be a new data set, so a new file for you. There's 2 files. This one is the felt on carpet as opposed to wood on table. And this one you're going to create a second graph to create another, determine another value or pair of values for the static friction coefficient and the kinetic friction coefficient for this combination of surfaces. All right, so let's zero the force sensor and let's try this out. Okay. Now, as we can see, there isn't really a great part where we have a difference in the static friction force. And so I'm going to try that again to see if I can actually get a better value. And if so, then I'll delete this trial from the data set, so you won't have to worry about it. But let's see. That's better. Okay, so something about my poll the first time around didn't quite do what it's supposed to, and that's okay. All right, so I'll make sure to delete that file from you. Let's save this whole thing as felt on carpet. Great. Okay, so this is going to be felt on carpet with wood. We will take dataset 1 and delete dataset 1. That way you don't have to worry about it, it's gone. All right, when we do the rest, I'll fast forward through all of this as well. All right, that's it for felt on carpet. Excellent. You may also be asking, well, what about surface area? It seems like if I had a large wooden surface area on the table, twice as big, then it would have more friction or less friction maybe than less surface area. Still wood on table, doing the same block, the same wood. We'll try this out and we'll see what happens. We're not going to do a full, 10 trials. I'll do 3 different trials, one with a block by itself, one with 4 newtons, and one with 9 newtons. And we can compare those values to see if it's significantly different from having the same block, the same normal force, but spread over a larger area, that larger surface area. All right, so we'll do that, and I'll give you these values, not to produce a graph or anything, just to compare those individual values to the first set that we did with the wood on the table to see if they're significantly different. All right, so zero my force sensor, and I hit collect, and I pull across the table. We'll do it again with 4 newtons on top. And then we'll do it again with 9 newtons balanced on top. Great. All right. We'll be able to compare those and see exactly how it works. Now that we've collected a bunch of data, we need to be able to analyze those graphs that I've given you. So to do that, you're going to load them into Graphical Analysis, either on your iPad or your own personal computer. Over on the left-hand side, you'll notice that it says force. You can tap that and it'll show you any one of the data trials or all of the data trials that we've collected. So the block by itself, the block plus 1 Newton, the block plus 2 Newtons, etc. Once you have that graph loaded up, you should be able to highlight a section of the graph either by clicking and dragging or tapping and dragging on your iPad over a section to just highlight a portion of the graph. Down on the bottom left-hand corner, you'll see a little button that looks like a graph. Tap that, that's graph options, and then you can do view statistics. Now, for that first section of the graph where you're looking at the static friction force, you want to find the maximum value, and it'll just say max, and read it in a value of newtons. Record that value for your maximum static friction force for that one specific trial for that one surface. A lot of data to keep track, so pay attention to what you're doing. Then, after you've done that, highlight a section of the graph towards the end where you have nice steady values while it was moving with a constant speed. We know then that that is equal to the kinetic friction force. And so you're going to hit the same graph options down the bottom left, hit the same view statistics, and then we see that there's a mean or average value for that force during that time interval. So as long as you get, a couple of seconds worth of data, then you can be confident that you're getting a nice even value that's going to be glossing over all of the bumps and divots along the surface to get a nice average value for the friction force for that trial. All right? Once you do that for all of your different data trials, then you should be able to produce a graph. That graph is going to be force on the vertical axis, two different kinds, friction force, static friction force, and kinetic friction force. And along the horizontal, it should be your independent variable, which was the normal force, determined by the weight of the block and any additional weight we put on top. The slopes of those lines should be very important to us. They'll tell us what the coefficient of static friction is and the coefficient of kinetic friction. You do that, record those values, answer some questions, and boom, now you know all about friction. Great. Good luck.